If you were floating in space right now, exposed to the vacuum, you would actually be warmer than you would be at the bottom of the ocean, and that sounds wrong because space feels like the ultimate cold, yet the deep ocean is colder, darker, and more thermally stable than almost anywhere else humans have ever measured, and the reason is not temperature alone, but how heat behaves, how energy moves, and how the planet quietly locks cold in place where sunlight can never reach. Because once you go deep enough, the ocean stops responding to the surface world entirely and becomes its own permanent climate, one that has survived ice ages, mass extinctions, and planetary warming without changing much at all. Why space is not as cold as you think. Space is often described as freezing, but space does not actually have a temperature in the way we experience it on Earth because temperature requires matter. And space is almost entirely empty, which means there are very few particles to carry heat away from your body. So in space you lose heat slowly through radiation rather than rapidly through conduction, which is why astronauts rely on thermal control systems instead of insulation alone, and why satellites can overheat even while orbiting a planet surrounded by darkness. The background temperature of space is about 2.7 Kelvin, left over from the Big Bang, but that number does not translate directly to how cold something becomes unless it is perfectly isolated and radiating energy away for an extremely long time, which humans never are, because our bodies, spacecraft, and equipment constantly generate heat. The deep ocean works differently, because water is not empty, it is dense, conductive, and relentless in removing heat from anything placed inside it. Water is the perfect heat thief. Water is one of the most effective substances on Earth at absorbing and transferring heat, which is why humans cool engines with it, regulate body temperature with it, and struggle to survive cold water immersion even at temperatures far above freezing. When you enter water, heat is pulled from your body about 25 times faster than in air, and this effect becomes more extreme as pressure increases and water density rises with depth. At the surface, sunlight constantly replenishes lost heat, but below a certain depth, that energy supply disappears completely, and once the ocean loses contact with the sun, it becomes a one-way system where heat can leave but never meaningfully return. The sun's hard limit, the photic barrier, sunlight does not penetrate the ocean evenly, and after about 200 meters, known as the photic zone, light rapidly fades until darkness becomes absolute. Below this boundary, solar energy is no longer a factor, which means the ocean beneath it cannot be warmed directly by the sun at all, regardless of surface temperatures, climate cycles, or atmospheric conditions. This creates a thermal ceiling, where the upper ocean behaves like weather, but the deep ocean behaves like geology, changing on timescales so long that human history barely registers. Why the deep ocean stays near freezing. Most of the deep ocean sits between 0 and 4 degrees Celsius, just above freezing, and it remains there not because it is constantly being cooled but because it is constantly being replenished with cold water formed near the poles. In places like Antarctica and the North Atlantic, surface water becomes cold and salty enough to sink, forming what is known as deep and bottom water, which then flows across the ocean floor like a slow, invisible river system. Once this water sinks, it is effectively trapped for hundreds to thousands of years, isolated from sunlight and surface warming, which means the temperature it carries becomes locked in place. Pressure makes cold permanent. As depth increases, pressure rises dramatically, reaching more than 1,000 times atmospheric pressure in the deepest trenches, and this pressure slightly raises the freezing point behavior of water while also increasing its density and heat capacity. Under these conditions, even if heat were introduced, it would disperse slowly and inefficiently, making the deep ocean extremely resistant to temperature change. This is why deep-sea temperatures barely fluctuate even during global warming events, and why instruments placed kilometers below the surface often record the same temperatures year after year. The thermal conveyor, Earth's hidden refrigeration system. The global ocean circulation system, often called the thermal conveyor belt, continuously transports cold, dense water from polar regions into the abyss, replacing older deep water and maintaining near-freezing conditions. This circulation operates so slowly that a single parcel of water may take 1,000 years to complete its journey, meaning the deep ocean you measure today may reflect surface conditions from before modern civilization existed. Because this system is driven by density rather than wind or sunlight, it continues regardless of atmospheric changes, reinforcing the deep ocean's thermal stability. Why even climate change struggles to reach the abyss while surface oceans are warming measurably. The deep ocean absorbs heat at a glacial pace, acting as a massive thermal buffer that delays and dampens planetary temperature change. This does not mean the deep ocean is unaffected, but rather that its response unfolds over centuries instead of decades, which is why most warming remains trapped in the upper layers for now. Ironically, this buffering effect makes the deep ocean colder than space in practical terms, because space allows heat to radiate away gradually, while the deep ocean actively strips heat from anything immersed within it. Human experience, why divers and submersibles struggle. Deep-sea submersibles require extreme insulation, heating systems, and pressure-resistant hulls not because the water is actively freezing them, but because it never stops pulling heat away. Early deep-sea missions reported rapid heat loss, condensation inside hulls, and mechanical failures caused by cold-induced brittleness, even in tropical oceans. This environment is so stable and cold that many deep-sea organisms have never experienced temperature variation in their entire evolutionary history. Why the deep ocean will always be colder than space. The key difference between space and the deep ocean is not temperature, but interaction, because space is passive while the ocean is active, constantly exchanging energy, enforcing equilibrium, and maintaining cold through circulation and pressure. Unless the sun itself changes or Earth loses its oceans entirely, the deep sea will remain a near-freezing environment, immune to daily weather, seasonal change, and even most long-term climate shifts. It is not just cold, it is locked into cold. The final realization: the deep ocean represents a world governed by physics rather than weather, by circulation rather than sunlight, and by timescales that dwarf human lifespans, which is why it can be colder than space while sitting beneath a warming planet, and why it remains one of the most alien environments humans have ever encountered, not because it is hostile, but because it is indifferent. The deeper you go, the less the surface world matters, and eventually, the ocean becomes a place where time slows, heat disappears, and the rules humans live by simply stop applying.